All right, here we're looking at section 8.2. So our learning targets are to graph quadratic functions of the form f of x equals ax squared plus c. So the difference here from what we looked at last section is now we've added this constant term at the end. And you'll notice this constant term does not have a variable with it. So we're going to look at what this does to our graphs. And then our second learning target is to solve real-life problems involving functions of this same form. Right, I still know that I'm dealing with quadratics because I have that x squared term. So let's look at our core concept. So here are the things that I know. I know that when I have this ax squared, that means I'm going to have a U-shaped graph. Okay, so when c is greater than 0, right, so if c is positive, my graph just moves up. And if c is less than 0, my graph moves down. And that also tells me how many units it moves. Okay, so I also care about the vertex. And remember, the vertex is where my graph changes direction. So my vertex, now that I have this c value, my vertex is that point 0, comma c. That c becomes the y value of my vertex, which makes sense because I've moved up and down. My axis of symmetry has not changed. My axis of symmetry of this is still going to be x equals 0. And that axis of symmetry is where I can fold my graph in half and it still be a mirror image of each other. So this c really just moves my graph up or down. Don't forget about my a. The a still stretches it or shrinks it, but the c just moves it up and down. So let's look at an example here. So I have to graph g of x equals x squared minus 2, and then compare it to my parent function of f of x equals x squared. So the first thing I want to do is I want to come up with a table of values. And these are the x values I always want to deal with, especially because I know my vertex is going to have be the x value of 0. So I start there, and then I go 1, 2, and then I pick 2 on the left side of it as well. So once I have this table of values, I plug in those x values for x and solve and come up with my y values. So now that I have those, I can plot my ordered points. Right, I've got 0, negative 2. I've got negative 1, negative 1, and I've got negative 2, 2. I also have 1, negative 1 right here, and then 2, comma 2. So you'll see my blue line is the new graph, my g of x. This black line is my parent function, or my f of x. So I was asked to compare the two, and what I know is different and the same. So I see that both of these graphs open up. They both have the same axis of symmetry, which is at x equals 0. The vertex has changed. My parent function vertex is at 0, 0, which is the origin. My new vertex, because I have this c value of negative 2, my vertex has moved down. So my vertex is now 0, comma 2. This is called a vertical translation, right? And vertical is up and down, and a translation just means I shift the whole graph up or down. So this is a vertical translation 2 units down of the graph of x. This is the most mathematically precise way that I can explain what I've done here. It's a vertical, so up and down, translation, which I shift the whole thing down 2. So now I've graphed it and compared it to my parent function. So here's your monitoring progress. Try them, see how you do. So now here's our next example. Again, I'm given 4x squared plus 1, and I have to compare it to my parent function of x squared. So again, the first thing I do is I make a table of values, and I start with my x value of my vertex in the middle, and pick 2 points on each side. I plug these values into my x, and I solve for my y. Then I've got my points, and I can plot those. And then I draw my smooth-ish curve. I know it's hard to draw a smooth curve when you're actually graphing on paper. And now I'm going to compare my two graphs. So the first thing I notice is they both open up. I know that they're both going to have the same axis of symmetry. I see here in my g of x, my blue function, that I have an a value that's different. So this a value, this is going back to 8.1, tells me that I'm going to stretch the graph by a factor of 4. So it's going to be taller and skinnier. Then I have a c value of this plus 1, so it's going to be a vertical translation up 1. That's what this tells me. So it's also telling me that my vertex has changed, so my vertex is now 0, comma 1. And then here's this last sentence. Here is our big sentence of comparing. The graph of g is a vertical stretch by a factor of 4, right? And that 4 comes from the a value. And a vertical translation 1 unit up. So everything here that we've looked at so far is dealing with our vertical, right? Up and down. So that's explained using this last sentence there. So here's our next example. So let f of x equal negative 0.5x squared plus 2 and g of x equals f of x minus 7. First I have to describe the transformation from f to g, and then graph them both in the same coordinate plane, and then write an equation that represents g in terms of x. Because you see right now, g is written in terms of f of x, so I have to have two functions here. So I want to write g where I don't need to see what f is. So the first thing I do is I come up with my table of values, right? And I can use the same x values for both functions. So I come up with my table, and then I plug them in and find both my f and my g, and then I can graph them both. So what I see is I have both of my graphs open down. They both have the same axis of symmetry. However, g is my vertex is now at -5 instead of at 2. And that's because I moved everything down by 7. So now I have to rewrite, I have to do part B, which writing an equation that represents g in terms of x. So I write the function for g, which I was given up here at the top. So I have f of x minus 7. So now I substitute what I know, and I know that this was the equation for f of x, and then I have my subtract 7, and then I subtract and simplify. So my equation for g in terms of x is negative 0.5x squared minus 5. So you'll see that it is a vertical translation down of my original graph. Here are your next monitoring progress. Try them. So now here's our real world problem, right? That second learning target. So the function f of t equals negative 16t squared plus s sub 0. This s sub 0 is my initial height, and I'm told that right here. So this function represents the approximate height in feet of a falling object t seconds after it's dropped from that initial height. So an egg is dropped from a height of 64 feet. So the first part I'm asked to figure out is how many seconds does the egg hit the ground? And then I have to figure out, suppose my initial height is adjusted, how will that affect it? So these I've already looked at. So when you're taking notes, you don't really need to write this down. Just think about, what am I looking at? The biggest thing is I know I'm not going to have a negative t value, right? Because that would tell me I have negative time, and that's just not possible. So now I have my function, and I'm told the initial height. My initial height is 64 feet. So I'm just rewriting my function with that information. So I have f of t equals negative 16t squared plus 64, which is the height of the egg t seconds after it's dropped. I also know that the egg hits the ground when my f of t equals 0. When my height is 0, I've hit the ground. So the first thing I want to do is I want to make a table of values. And here you see I only have positive values in my t. I don't care about negative ones because I can't have negative time. So I make my table of values, and then I plot my points and sketch my graph. So I see both from my table and my graph that I have a 0. And a 0 is the same thing as a root, which is the same thing as a solution. It's where my graph crosses the x-axis, or in this case, the t-axis. So the positive 0 of the function is when t equals 2. So my 0 is 2. So this tells me that the egg hits the ground 2 seconds after it's dropped. So now for part B, when the initial height is adjusted by k feet, the graph is moved. So I think about this as if I then stand on a ladder on top of the building, right? My initial height is a little bit higher. So I have my k is a little bit more positive here. So if I translate this entire graph up, my 0 is going to be a little bit after 2. And I want to think about this logically too. If I'm taller than the building is, it's going to take a little bit longer for the egg to hit the ground. And also, if I know my k goes down, so if I don't go to the very top, if I only go to one of the stories and I drop it out the window, my entire graph will shift down or translate down, and so it will hit sooner than 2, which again makes sense logically, because if I'm not as high up, there's not as much distance for the egg to fall, so it will hit the ground faster. Okay, so when k is greater than 0, right, so k moves up, the egg will take more than 2 seconds, and if k is less than 0, so if I go down, the egg will take less than 2 seconds. So we can think about this mathematically, and we can think about it logically as well. So here's your final monitoring progress. Now we're going to look back at our learning targets. So our first one was to graph quadratic functions of the form f of x equals ax squared plus c. Now remember that this c value just moves my graph up or down. So I always want to look here first and see my stretch or my shrink, and then I can translate my graph up and down. And then we were solving real-life problems involving functions of the same form, f of x equals ax squared plus c. And again, what happens when I change the c value? If I go more up or more down, we can tell what happens to the entire function. So now that we've gone through this, go ahead and work on your homework for section 8.2.